My name's Eli Schwartz, and I'll be leading you through this second portion of the algebra skills that you need to know for the GED for test day. We'll be covering these three main learning objectives. Understanding and applying larger, more complicated polynomials and expressions can be a little bit daunting at first, but we'll take it piece by piece and see how some questions might look like they're asking you for a lot more than they actually are. Then we'll be dealing with writing and multiplying, foiling, factoring, and computing things with quadratics, and finally finish out with evaluating functions, including maybe evaluating some functions that look at first rather complicated. Let's dive right in. When we talk about evaluating something, or factoring, or foiling, or quadratics, we're really talking about applying a polynomial math. Polynomial just means you have multiple terms in it. So this term, 3x squared, is one part of a polynomial. When we have the 7y plus 8, all of those added together gives us this large polynomial. Each term might have a coefficient, a variable, an exponent, any of a variety of pieces. For example, in front of the x squared and in front of the y are the coefficients. The actual x or y themselves are the variables, and if there is an exponent, well, a square or a cube is the exponent. Now, also in this, as in many polynomials, there's something that doesn't have a coefficient or a variable on it, and that is the constant. Constant is just the main whole number that doesn't have anything applied to it. Now, if there are exactly two terms, we actually have a special name for that. That's a binomial. And we'll talk about this more in quadratic expressions. Often we're dealing with a binomial expansion. So an x plus 7 or a y minus 4 or something like that. Now, in a polynomial math expression, we're often combining like terms first to try and simplify, then, if possible, continuing to combine for exponents or combine for value. For example, x squared terms, even if it's a positive and negative, can combine together. Y squared terms can combine, but they can't combine with a y to the fourth. So in this top row, 8x squared plus negative 6x squared does combine and gives us 2x squared left over, but 9y squared and 9y to the fourth can't combine together any simpler. They would just stay as is. Now, anytime we're adding and subtracting, we go through systematically making sure the variable is the same and then adding or subtracting the coefficients. Like I just did out loud, we have it down here at the bottom of the screen. Now, if we are doing a solution, multiplying, dividing, or solving for something, we are still often dealing with the coefficients first, but we can potentially divide by variables as well. For example, in this case, I have 2 being divided into the entire expression 4x squared minus 8y cubed. The 2 divides in to each of those pieces separately, sort of like distributing, but we're distributing across a division instead of distributing multiplication like we normally do. So the 2 distributes in to the 4x squared and it distributes in to the 8y cubed. Now, dividing each of these coefficients by 2 gives us 2x squared minus 4y cubed. Now, we can certainly divide by a variable, and when dividing by a variable, again, we're canceling or simplifying as much as possible. In this example, x is being divided into the upper expression, the same expression as before. In this case, the x can cancel against another x. Think of this like 2 canceling a 2, or 10 canceling a 10. A variable really just represents a number, so it's okay to cancel. The x then cancels against the 4x squared, leaving just 4x remaining. But x can't cancel against y, they're different variables. So that term stays as is. It doesn't simplify any better. As always, if we're dividing by something, because a variable represents any possible number, it's worth reminding us that we can't divide by 0. So if there is a situation where we're dividing by a variable, and that variable ends up potentially being 0, that invalidates the expression. Dividing by 0 is undefined. Now, when we're dividing by something a little bit more advanced, a larger polynomial, the same rules apply. Divide out the coefficients if possible first, divide out similar variables against similar variables, and whatever we're left with, try and simplify as much as possible. Let's try it with this one. In this case, the 6x squared y is going to divide into the first and second term on top. So it might make sense, even just for scratch work, to separate them out right now. Now, once they're separated, again, normally we would go systematically. Let's start with coefficients. The 6 dividing into 8, well, we could simplify that down into 4 over 3. And 6 into 6, well, that cancels completely. Now, often we don't write in the 1, but we put it in here as a placeholder just to remind you it did cancel completely, it did divide out completely, and the 1 is kind of by default represented there. Now, we could go to the y terms or the x terms, but arbitrarily, let's take x terms next. The x squared cancels against x to the 4th, leaving x squared remaining. And then the x squareds on the second term cancel completely. Again, we'll put in a placeholder 1 just to remind us this is where it came from, but on test day, and certainly on your scratch sheet, there's no need for you necessarily to do that. The 1 is implied. Last up, the y terms. In this case, the left term completely cancels out y, and on the right, we have the y canceling into y cubed to be y squared. Now, in total, again, we get rid of all of those 1s that are placeholders, it would look something like this. 4x squared divided by 3, all plus y squared. It looked like it was pretty complicated at first. It definitely took a lot of careful steps to get to the end, but this is the sort of problem that looks like it's going to be very complicated, and if we're systematic, we can get through it, hopefully without too much trouble, and earn that point for the time we've put in. In fact, let's put in a little bit of time on this question. Freeze the video, take some time to try it yourself, and then we'll review it together. So for number 1, we want a simplified form of an expression that often means that there's at least one or more like terms. Let's look for those like terms. I see an a squared times b that actually happens to have exactly the same coefficient. That doesn't have to have the same coefficient, but that does make our life a little easier. Combining those together, 3 plus 3 is 6, so we have 6a squared b. Now, looking at the rest of the terms, they actually both are ab. Again, we don't have to have a lot of like terms in a problem, but whenever we are simplifying, we're always on the lookout for them. Again, combining means combining the coefficients together, leaving the variable as is. That gives answer choice D, 6a squared b plus 9ab. Watch out, some of these other answer choices look like they're also maybe adding the exponents of the variables, like answer choice A or C in some weird way. The only time we add exponents directly is if we're multiplying things that have the same base or the same variable. We're not doing that in this problem. We are adding, so adding keeps the variables as is. Let's try this again on another problem where we're trying to simplify and then count how much we've simplified. Go for it. For number 2, not only do we have to simplify, but then we have to find out what are the different terms in the end. So we don't technically have to do the entire work on this problem. We just have to look for different variables or different powers. In this case, there's a j squared term. I'll write that down. There's a k cubed term. We'll write that down. And then a j cubed term. Now, we don't have to go through and actually do the addition or subtraction or truly simplify, because we know if there's a like term, those like terms will combine together. That means there are 3 different terms total. With answer choice B. Again, saving ourselves some time from doing what looks like it would actually be a little bit of bookkeeping, a little bit of careful math, ends up being a little bit simpler once we look for what's actually being asked in the problem. Next up, For problem 3, and the last one we're going to try before moving on to our next topic of multiplying binomials, freeze, take your time, watch out for positive and negative signs, and then we'll review together. Now I mentioned, watch out for positive and negative signs because on this problem in particular, that's one of the most common mistakes that people make when going too fast or rushing the work. Anytime we have a subtraction of a term or a negative being distributed across a parentheses, I'm always on the lookout for a careless mistake. So what I would do first, before even trying to simplify directly, is I would distribute the negative throughout to make sure I didn't make a mistake. So the 5x squared minus 2x plus 1, that stays as is, but then simplifying the parentheses by multiplying out that negative. So the negative applies to the 3x squared. That negative 3x becomes a positive, and negative 2 becomes a positive. By far the most common mistake here is often just multiplying the negative to the first term instead of distributing across the entire thing. Watch out, easy mistake to make. Now, rearranging, I could put the like terms close to each other. So the 5x squared and the negative 3x squared, because those are both x squared terms. Similarly, the x terms or the whole value terms. I don't have to put them all together, but grouping them together like this lets me really clearly see that I've transposed them from one place to another, and I can actively just add or subtract those directly. Again, not necessary. Certainly if you're running out of time on your scratch paper or running out of room, I might skip this and just kind of go through systematically. But if you've got the time, rearranging helps make sure we don't make a careless mistake. Now, that does match exactly to answer choice C as in champions. I will just remind you before we move on that something like answer choice D is exactly the answer we would get if we distributed the negative into the first term and the last term, but forgot to apply the negative to that middle term, the negative 3x. That would actually give us answer choice D when adding them together. So remember, wrong answer choices are often the result of a quick mistake or a sloppy mistake that we can definitely fix and solve for test day, but we do want to be on the lookout for it. Now I promised we were going to dive in with multiplying binomials. This is the FOIL method that you may have seen in class. FOIL stands for first, outer, inner, last. And we've talked about that last problem. The most common mistake we tend to see students make is distributing incorrectly. Distributing only to the first term, distributing to the first and last, but forgetting the middle, any of a variety of things. So now we're distributing across a binomial. That means not only do we have to track that each term gets distributed onto in the second parentheses, but that each term gets distributed from in the first parentheses. I know that sounds a little bit complicated, but that's what FOIL solves. The first two terms match up, so we don't forget them. That gives us 2x squared. The outer two terms match up, which gives us negative 10x. The inner two terms give positive 3x. And then the last two terms gives negative 15. This is what we mean by first, outer, inner, last. It's really just a way to carefully check that we actually distributed all of the first binomial across all of the second binomial and didn't miss something along the way. Now, combining the like terms, in this case the x term, gives us 2x squared minus 7x minus 15. That's the expanded form or the FOILed form of the original binomials we multiplied. Let's give it a try. On question number 4, pause, use FOIL to solve so we don't make a mistake along the way, and then we'll review it together. All right, for 4, as always, whenever we're expanding out a binomial, we will use FOIL to make sure we didn't miss something. So the first term is 3x times x, which is 3x squared. The outer terms gives us a 6x. The inner terms gives us an 8x. And then the last terms gives us plus 16. Combining the 6x and 8x gives 14x, which is a perfect match to answer choice B. 3x squared plus 14x plus 16. Again, as you're going through and solving, It's important to carefully keep track of each piece. As you get faster and faster at foiling, it may be tempting to immediately combine, in your head even, to try and get that 14x middle term. While that's fine to do, if you're feeling very confident, often we still recommend write it down in long form. Write down every single term on the scratch paper. That way you can double check, make sure that you don't accidentally fall for one of the other wrong answers, which might have a positive or a negative flipped from what you would otherwise have done. Now this is going in one direction. Foiling is expanding the binomial, multiplying it out, distributing it out. We can actually go the opposite direction. That would be factoring. Occasionally you might be asked to factor an expression, which is just going all the way back to the original terms. Often this is done to find a root or a zero of a function, but they could just say factor this expression. So if we started with this expression, we know from the work with foiling that two things had to multiply together to give us the x squared. But also, two things had to multiply together directly to give us the negative 15. That's actually a better place to start. The negative 15, well, that's got to be two numbers that directly multiply to give us that negative 15. It could be a 1 and 15, and of course, one of them would have to be a negative. It could be 3 and 5, and again, one of them would have to be negative. Or flip-flopped, right? Whichever one was negative before could be flipped to positive. So these are the pieces that would have to multiply together using whole numbers to give us that negative 15. And we assume until told otherwise that we are multiplying out whole numbers, and especially because that 2 in the middle term adds up to such a clean value. It's not 2.25 or 2.71 or something messy. Well, then that means that positive 2 was from combining like terms. When we FOILed out whatever this thing is we're solving for, we would have gotten those two values, then combining those like terms would give us the positive 2. So which row in the table we just made gives us two values that when we add them together, the sum is positive 2. Looks like negative 3 and 5. So negative 3 and 5 are what has to go inside the binomial. So this is how that binomial must have originally looked. And we can also FOIL it back out. Foiling this back out had better give the original expression we started with at the top of the screen. Let's double check. X times x is x squared. Yes. X times 5 is 5x. Negative 3 times x is negative 3x. And negative 3 times 5 is negative 15. Adding those and combining like terms does give us x squared plus 2x minus 15. Whew, good thing we double checked. Now, again, this is a great way for you to double check your work, but it's also a way that we could start from the answer choices and check each of them systematically if we were really not feeling confident in going quickly through a factoring on test day. Either one of those, you should try for number 5. Either directly trying to factor or using the answer choices to get close. Good luck. Let's take a look. My preferred way to do this would be the direct math, trying to solve for what we could multiply together to give us the 16 should allow us to start finding the values inside each binomial. So 1 times 16 would work, 2 times 8, 4 times 4. Even at this point, I could probably get rid of C and D. In C, 4 times 6 is 24. That's not right. And in D, 10 times 16 is 160. That's also not right. It actually has to be A or B already. They're the only ones that have part of the binomial where the second term would multiply to actually give 16. That's a good elimination, and if I was short on time, it would have gotten this down to a 50-50 guess if I had to guess and move on. Now, we don't have to guess, because we know the next step. Which of these adds up to be positive 10, since that's the middle term in the expanded form? Well, 4 and 4 doesn't, but 2 plus 8 does. So it must be that the factored form is x plus 2 times x plus 8, and that's a match to answer choice B. Now, as a reminder, we could have actually, especially after getting rid of C and D, just taken A or B and FOILed it out. Whichever one gave the correct answer that we started with would be the right answer. And if one of them clearly gave a wrong answer, we also know a third wrong answer. If you can work on a problem and get rid of 3 wrong answers, whatever you're left with must be the one right answer. It's a nice way to do it as well. Now, last up, in terms of application, the reason that we might want to factor is because we're solving a quadratic expression, or solving that expanded form. You might want to solve if we're trying to find which values give us 0, what are the start and end points of a relationship, what are the values that you'd have to sell in tickets or apples or goods in order to break even. These are all variations of a 0 problem. So let's suppose we took that problem from earlier, and we were trying to solve for the zeros, or solve for the values that make this true. Now, we've already done this, but we would be factoring this out. So factoring it to the x plus 5 and the x minus 3 form, and then truly solving is solving for each of those parentheses. So the x plus 5, if that term could become a 0, then the whole expression is 0, because 0 times anything is 0. So if we took that piece, that solves to be x equals negative 5. If x is negative 5, then that is a 0 of this expression, meaning the whole expression becomes 0. Similarly, x minus 3, if that piece is 0, then similarly the whole thing is 0. So that means x equals 3 is also another solution. It's another root, or another 0. We would write that out by just saying x equals negative 5 and x equals 3 are roots of the equation, or solutions of the equation, or zeros of the equation. Any of those are really the same thing. Let's try this for problem number 6. Go ahead and freeze, attempt to do the factoring, solve for the 0, and then we'll review together. Now, there's something a little bit sneaky on this problem, and the sneakiness is, if you notice, answer choice A, C, and D all look very, very similar. Positives versus negatives have been flipped around a little bit, and if we were going a little bit too fast or maybe carelessly, we might end up with an exact wrong answer on this one. So careful scratch work, paying attention to signs is of the utmost importance. Let's dive in. If we're factoring, the first step in factoring is deciding what could multiply together to be negative 12. That's 6's and 2's, or 3's and 4's, or 1 and 12, but no matter what, because it's a negative, half of it would have to be negative. Positive 12 and negative 1, or negative 2 and positive 6, whatever it is. The second piece, though, is they have to add, when we combine, to be 4, because that middle term is 4x. So I have to have numbers relatively close together, like 6 and 2, and they have to have the positive 1 be bigger. So negative 2 times positive 6 does give us negative 12, and negative 2 plus 6 leaves that remainder of 4 being positive. Now, that negative 2 and positive 6 is not the answer we're looking for. Answer choice C is probably the most commonly chosen wrong answer by factoring correctly, but not solving for the solution. The solution is when x minus 2 is 0. So that would be a positive 2 value. And then x plus 6 equaling 0 would be a negative 6 value for x. That's a match to answer choice D. And again, C is a very tempting wrong answer, as potentially is A, by going through and doing the majority of the math right, the factoring correctly, but then at the end, not actually solving for the solution. In this case, we're solving for a particular value, x equals 0, or y equals 0, or the function equals 0 at the end, and that particular value is the function value. The input, x, has to give us out in this question an output of 0 to truly be the solution. But any output is a set of values that a function could give us. A function really just means here's a rule, here's an expression, here's an equation, that gives us something. So if I input a distinct value of x, I output a distinct value of y, or f of x, or whatever the expression is. So if I was selling scarves, let's say, every scarf that I sold, I should make some money off of. Even better, if I'm selling lots of scarves, I might give a discount. So if you buy more scarves, you don't have to pay quite as much. So every input of scarves sold outputs a particular discounted price that someone might have to pay. What you see on screen is, well, a function. Every input, x, gives us an output, in this case, cost per scarf for that many scarves sold. And going a little bit deeper, if you have a named function, the letter in front of the parentheses x called the name. So in this case, f is the function name. This is an f function. Often we have f or g or ABCs. Those are often function names, pretty early letters in the alphabet. X is the input, it's the thing we're putting in. We might also just say x is the main variable. X is the direct thing that we can affect. So then f of x is the output, the thing we get back out, the thing that changes as a result. Often we just shorthand f of x and call it a y value. This is the dependent variable. X is the independent variable. So given an input of some independent variable x, we get out an output of something. In this case, 3x plus 2, which is our y value. I know this might all seem a little bit high level and a little bit theoretical, but we can plug in a value. If we plug in 4 for x, then that just means put 4 everywhere there's an x. So 3 times 4, which is 12, plus 2, which is 14. So f of 4, or the function of 4, or the y value when you plug in 4, is equal to 14. Let's try this out on a problem. For number 7, pause, maybe consider rewriting even the expression on your own scratch paper just so you have it in front of you, and then make sure to carefully apply the equation. Good luck. Now this one appears to be a lot more work at first than it maybe ends up being. A long paragraph at first, a lot of setup for the actual expression, but at the end, what they're really asking for is to take this expression that they already gave and then plug in for a smoke guard price of 89. Now smoke guard is the S value, so 89 plugs in for where there was an S. Do the thing in parentheses first, that gives us 74, and then do the final addition, that gives us 99. Answer choice A. This looked like a very tedious problem, a lot of work up front, a lot of steps potentially, but in the end, a function problem may just be plug in for the x value and get out the function. Similarly, problem number 8 requires us to do a little bit of function math. Give this one a try. All right, so for this one, there is a cost of $255, and we're still applying that functional price. S is the cost of any additional services. So a new damper is another S value. Plug in 255. So doing the parentheses first subtracts out 15 to be 240. Adding into the total net gives 265. Answer choice B. Again, if this had been a brand new problem or a brand new paragraph, it might look a little daunting at first, but plugging in for a variable, even in a complicated looking expression or function, often just means solving for the x or solving for the y by plugging in one discrete value. That may even be a value that you feel pretty comfortable with, or a function that you've seen before. For example, if you've been in some chemistry or physics or even biology classes, you may have already seen these expressions for Celsius to Fahrenheit and Fahrenheit back to Celsius. Now, this is not something you have to have memorized for the GED, but it is something that is a pretty common expression, and it's something that might come up again. Give it a try. All right. In this case, we're kind of tasked with deciding which formula we want to use. Both formulas have a C value and an F value built into them. And both of these would work to solve. The only real question is which one would be a little bit simpler for me to do the math on. So for me, because I want to know the temperature in Celsius at the end, I might as well just use the first expression that already has Celsius equals some math. Again, technically, I could plug into the other expression, multiply and divide and do all of the work to get Celsius by itself in the end, but why not start with the expression where it already is separated? Plugging in 68 for F, subtracting the parentheses first, and then multiplying by 5 and dividing by 9. And as a heads up, I would probably divide by 9 first, because I know that 9 goes into 36, leaving 4. Then I can multiply 5 by 4, giving 20. Answer choice A. As an additional note on this problem, if you are already familiar with Celsius and Fahrenheit, you know this off the top of your head, maybe you have used a lot of Celsius and Fahrenheit interchangeably for different systems of temperature, you can solve this problem directly. If you know the answer that 68 degrees Fahrenheit is about 20 degrees Celsius, that should be the answer. The GED is not going to, on purpose, objectively take a true statement of temperature or time or distance and then make it wrong on testing. So 68 degrees Fahrenheit should be 20 degrees Celsius anyway in the real world. That should be the answer to the formula they give you. Let's do another practice problem. Again, focusing in on this last one on careful systematic scratch work. Good luck. Now, there is a short note here at the beginning. If x does not equal 0, often we just read past that because x equaling 0 would invalidate the expression. It would make it undefined. But this is a placeholder statement they basically have to say in order to remind you, hey, the x's could cancel out. They could be divided out. They're not zeros. We're just going to put this in here to cover ourselves. The rest of the problem is really what we care about. Simplify an expression. All right, we're dividing by an expression that has both a coefficient and a variable, and we're dividing it into something on top that's a polynomial, which means we have to carefully divide that denominator into each term of the numerator. Might as well write that out carefully and then do each term separately. The 3 in the first term divides into 18 to give 6, and the x cancels out on x squared, giving x remaining. The 3x also cancels directly into the 6xy, giving 2y remaining. That's a perfect match to answer choice A. As always, careful systematic work is the key to these problems, and it could be easy to fall into a trap of one of these other wrong answers if we had gone really quickly and forgotten to cancel or forgotten to divide one of the terms. As always, the main goal of these sessions is really to focus on effortful practice against learning objectives. Learning to efficiently evaluate and compute polynomial expressions, to divide or multiply, to FOIL for a quadratic, or to solve for the 0 for a larger expression. And then evaluating a function is really plugging in for that value, but it may mean that you had to FOIL first, do some binomial expansion, then plug into a value to actually get that in the end. While these do tend to be a little bit more complicated problems in terms of the work being done or the concrete math or scratch work, they are not necessarily higher difficulty problems if we can be systematic and careful. A big part of being systematic and careful is just putting in that effort up front. So as always, putting in the time to practice these can help you avoid multiplying negatives across a distribution problem, missing one, can help you avoid accidentally forgetting a variable that cancels, and be sure that the work you've put in is guaranteeing you the points back out that you deserve. Good luck practicing.